Hello everyone, welcome back to section 14.5, directional derivatives and gradient vectors. So we're going to start out by talking about how the gradient vector can relate to level curves and directional derivatives along level curves. So first, why don't we just review what a level curve is. So for a level curve, we need a function of two variables, and these are the curves where that function is constant. So here I've just plotted some level curves for the function x squared plus y squared. This is a paraboloid, a bowl shape. And so curves where this bowl is shaped, the function value is constant, give us circles. So this is where x squared plus y squared equals 2. We get that circle. Here's where x squared plus y squared equals 4. We get that circle, etc. So these are all level curves of that function. The function is constant on these circles. So how does that relate? How can we relate directional derivatives and gradients to these level curves? Well, if our function is constant along this level curve, that means f of xy is equal to some constant, the directional derivative along that curve is 0. So think about if you were standing on some surface and you looked in the direction of a level curve, that surface would not be increasing or decreasing, it's constant. It would be flat along that curve. So therefore the directional derivative is 0. Okay, well, what if we can find a parameterization for a level curve, call it r of t, and then we define the unit tangent of that level curve. So we have to assume that this level curve is smooth, meaning it has a derivative and it's non-zero everywhere. Then the unit tangent vector, capital T, is going to be the direction vector for that level curve, kind of like the u in our definition of directional derivatives. So now if I take a directional derivative along this level curve, it has to be 0, right? We just said that. Directional derivatives along the level curves are 0, so that means that the gradient of f dotted with the unit tangent has to be 0. This is telling us that the gradient is orthogonal to the level curve. And this is always going to be the case. So we have this important property. The gradient vector is always orthogonal. It's perpendicular to level curves and level surfaces. It's the normal vector to these curves and surfaces. So for a function of two variables, if you set a function of two variables equal to a constant, you get a level curve. The gradient vector is orthogonal to that curve. If you have a function of three variables, you set it equal to a constant, you get a level surface. And the gradient vector is orthogonal to that surface. It's the normal vector for that surface. So let's see a quick example. Take these same level curves here. And now if I calculate the gradient of x squared plus y squared, it's 2x, 2y. That's the x partial derivative, y partial derivative. And now I plot a bunch of those gradient vectors on top of my level curves. You will see that these gradient vectors look like they're perpendicular to these circles. Right? I would have to draw some tangent lines. These would all be orthogonal to those tangent lines. So that's how we tell that the gradient vector is orthogonal to the curves. But you can see that from the plot. Now if I look at a level surface, this is just the surface from our example in the last video that we took a directional derivative of. And now at that point where we were taking a directional derivative, I've plotted the gradient with this arrow. So it might be a little more difficult to see, but this arrow is orthogonal to the surface. This vector is orthogonal to the surface. If you have a more curved surface, that might be more difficult to see. So how can we define something rigorously? That's how do we say something's orthogonal to a surface? Right? For curves, we say it's orthogonal to a curve if it's orthogonal to the tangent vector. So do we have something analogous for surfaces and things in 3 dimensions? And we do. Now we get the idea of tangent planes. So a tangent plane is a plane that is tangent to a surface, right? Just like a tangent line. So it intersects the surface at one point and does not go through the surface near that point. Right? So here's a crude drawing. if this bubble is my surface, I pick some point and I draw this plane that's tangent to the surface at that point. Now this tangent plane contains all possible tangent lines. That means that if I look in a certain direction and draw a tangent line in that direction, it has to be in the tangent plane. So this plane contains all possible tangent lines at that point in any direction. And the normal vector for this tangent plane, so a vector that's orthogonal to the plane, orthogonal to all vectors in the plane, is the gradient. So for tangent planes, the gradient is the normal vector. And so that's how we can define something that's orthogonal to a surface, if it's the normal vector for a tangent plane at that point. So it's orthogonal to the tangent plane. And that's how the gradient is orthogonal to a surface. Now, how do we write the equation for a tangent plane? Just get rid of this. The equation for a tangent plane to a level surface at a specific point. So let's say our level surface, we have a function of 3 variables equal to a constant. That's how we get a level surface. And we have some point, x naught, y naught, z naught. It's a fixed point. The equation for our plane, we have the components of our gradient, right? This is just the partial derivative with respect to x, y, and z, evaluated at the point x naught, y naught, z naught. Well, they're all there. So these are just numbers. Each one multiplied by x minus x naught, y minus y naught, z minus z naught. So here x, y, and z are variables. X naught, y naught, z naught, again, are our fixed point. So this is the same as, get my cursor out of the way. My apologies. The same as the equation for a plane that we saw in chapter 12, except now the components of the normal vector are the components of our gradient. So we could rewrite this tangent plane as the gradient evaluated at a point dotted with this vector x minus x naught, y minus y naught, z minus z naught. Now before we go on, if I were to cover up this z component and ignore these z naughts, so pretend that z naught's not there, pretend that z naught's not there, now I have a function of 2 variables. This would be the tangent line, so the line tangent to a level curve. They give that formula in the book. We're not going to focus on it too much, but it's basically the same thing, just in 1 dimension less. So if you have a level curve, you're not going to get a tangent plane to a level curve. You're going to get a tangent line to a level curve, and that gives you the formula. So those are tangent planes. We can also define a normal line using the gradient. So a line that's orthogonal to a surface. So not just a vector, but a line going on forever in both directions. So to define a normal line using the gradient, we still have a fixed point. So we're starting at this point. T is our parameter. It tells us how much we're going in our direction. And the gradient is our direction vector. So again, the gradient is going to be orthogonal to that surface. This is telling us we're going in an orthogonal direction. And t can take, if it's the entire line, t can be any real number. If we want to make a line segment, we would have to truncate t at some point, but for now, let's just look at the entire line. So this is the normal line to a surface. If I want the normal line to a level curve, I can just do what I did before, cover up this z component, get rid of those z naughts, and that gives you a normal line to a level curve. Okay, now let's finish up section 14.5 by doing an example of finding tangent planes and normal lines. So let's say this is our level surface. We have z squared minus 2x squared minus 2y squared equal to 12. So this is our function of 3 variables, f of x, y, z. This is our constant 12. And I want to find the equation of a tangent plane at the point 1, negative 1, 4. So the first thing I'm going to do is I'm going to calculate the gradient. So I'm going to take the partial derivative with respect to x, which is negative 4x, the partial derivative with respect to y, which is negative 4y, and the partial derivative with respect to z, which is 2z. So we get the gradient there. negative 4x, negative 4y, 2z, and then I plug in the point where I want to define this tangent plane and normal line. So I need to evaluate my gradient at this specific point, 1, negative 1, 4, and I get that the gradient at that point is negative 4, 4, 8. And now it's just a matter of plugging the right numbers into the right places, right? So here is my tangent plane. I have negative 4, which was the partial derivative of f with respect to x, times x minus 1. 1 was my x naught, plus 4, which was my partial derivative of f with respect to y, times y plus 1. My y naught was negative 1, so y minus negative 1 becomes y plus 1, plus 8, which was my partial derivative with respect to z, times z minus 4, which was my z naught. So there's my tangent plane. You can go ahead and simplify this, right? Distribute everything through, combine your constants, get them on the other side, and then you can even multiply this plane by any other constant. Remember, we can multiply equations of planes by constants. It still represents the same plane. So if I were to divide everything by 4 or negative 4, I get the same plane. I could multiply by 20. That would still give me the same plane. It would just look different. So I can, I guess you could say simplify, but there's no reason why this is simpler than the other, just the fact that the numbers are smaller. I've basically factored out the common factor. So x minus y minus 2z equals negative 6 is the same plane, but there are infinitely many ways you could represent this. Now for the normal line, we're just going to plug the numbers straight in. Right, so the x component of my normal line is x naught minus the partial derivative of f with respect to x times t, so 1 minus 4t. The y component is negative 1 plus 4t, the z component is 4 plus 8t. So here, the fixed point are my constants, the gradient are the coefficients of t. And I have a vector equation. It's a vector function of one variable with 3 components. That maps out the line. Now here, you could use any scalar multiple of the gradient. That would give you the same line. So instead of negative 4, 4, 8, if I wanted to use negative 1, 1, 2 for these coefficients of t, that would give me the same line. That's fine. You're just basically changing how you're parameterizing the line. But it gives you the same line. Now, let's take a look at a visual representation of these. So here's that surface. Z squared minus 2x squared minus 2y squared equals 12. It's just another paraboloid, another bowl shape. And now I'm going to draw the tangent line the tangent plane on top of that. So here I've used x minus y minus 2z equals negative 6 as my tangent plane. And you can see that I get a plane that is tangent to this bowl shape. Doesn't go through. It just hits at one point. Now, it might be more difficult to tell, especially with me moving it around and hopefully not making you all seasick. They intersect this surface at the point 1, negative 1, 4. So this is x equals 1, y equals negative 1. That's definitely more difficult to z equals 4, but that is the point 1, negative 1, 4. Now, if I were to draw the normal line, I get this line that goes through the point 1, negative 1, 4 and is orthogonal to the surface. Again, it's difficult to see it's orthogonal to a curved surface, but what this is saying is that this line is really orthogonal to this plane. And that's how it's orthogonal to the surface. And then there's the equation for the line that we had in the notes. 1 minus 4t, negative 1 plus 4t, 4 plus 8t. So that's going to wrap it up for section 14.5. The next video that you'll be watching for this class will begin section 14.6. And I will talk to you all later.